right. Good morning, everybody. Welcome back. So for today, let's talk a little bit about trends in compounds formation. So we are going to use the electron configuration that I showed you on Wednesday to figure out how the elements will combine with themselves to achieve some sort of stability. So most of the compounds in nature are found as a combination of different elements. For example, potassium by itself is highly unstable and reacts violently with water, while salts such as potassium carbonate or potassium chloride are extremely stable compounds. Okay. So for example, here, this shows the reaction between potassium and water, so a very exothermic reaction. While potassium carbonate, that's a very stable compound, it will not react or decompose by itself. Okay. So different compounds are grouped in classes as a function of their bonding. Okay. That's the important topic today. And we will start with two major classes: ionic compounds and covalent compounds. Okay, so everything in nature will try to achieve stability. Okay, this can be achieved by bonding within the same element or with different elements. So let's go back to nature and see what is the standard for stability. Noble gases or elements from the group 18 are found isolated in nature. So that means noble gases by themselves, they are stable. So any other element will try somehow to imitate what a noble gas is to achieve stability. And that is called octet rule. Okay? So let's take a look at the noble gases. Let's do the electron configuration of the noble gases, and let's see what do they have that's special and that will render stability. Okay, so ignore helium at this point. So let's look at neon, argon, krypton, xenon, and radonium. Okay? And I want you to direct your attention to the valence shell for the noble gases. Okay? So remember that valence shell is the very last filled shell. So let's highlight the valence shell for neon, argon, krypton, xenon, and radonium. Okay? So if you look at just the valence shell, all of them have one thing in common, which is 2 plus 6, 8 electrons in the valence shell. Okay? And that's the octet rule. Any element will lose or gain electrons to acquire the stable noble gas electronic configuration. In other words, any element will try to lose or gain electrons to achieve 8 electrons in the valence shell. And that's the standard for stability. And here we are always going to look at the valence shell. Okay? That's the important part. All right, very good. Okay, so let's take a look at potassium, bromine, oxygen, magnesium, and nitrogen. Okay, so the first thing I want you to do is to locate those elements in the periodic table. Okay, see which group they belong, and from that we are going to figure out the number of valence electrons. Remember that the number of the group is exactly the number of valence electrons that you have. So let's start with potassium. Potassium is in the group 1. Therefore, we have 1 valence electron. Okay. Bromine. Bromine is right here in the group 17. An important detail here, when we are in between groups 13 and 18, we are going to subtract 10 from the group number to get the number of valence electrons. Pay attention to that. Therefore, 17 minus 10, that will yield 7 valence electrons. Oxygen. That's in the group 16, right here. Again, 16 minus 10, that will give 6 valence electrons. Magnesium. Group 2. So therefore, 2 valence electrons. And finally, nitrogen, group 15. 15 minus 10, that's 5 valence electrons. Okay, so knowing the number of valence electrons, now we have to figure out if it is easier to gain electrons to get to 8 or lose electrons to get to 8. Okay, so let's look at potassium. Only 1 valence electron. Now ask yourself, is it easier to gain 7 to get all the way to 8 or just lose 1? Lose 1 is much easier, right? So therefore, potassium will achieve stability when 1 electron is lost. If we lost 1 electron, that means we have now a positive charge, and the number of the charge is equals to the number of electrons that were lost. Okay? So therefore, potassium plus is stable. Now let's look at the complete opposite. Bromine has 7. Again, you can gain 1 electron to get all the way to 8 or lose 7. Which one is going to be easier? Just gain 1 and we get all the way to 8.
It's the latter.
Yes? One electron is gained. Every time we gain electrons, we will acquire a negative charge, and the magnitude of the charge is exactly equals to the number of electrons gained. Now let's look at oxygen, the same line of thinking, 6 valence electrons. We need to get all the way to 8, so we can either gain 2 or lose 6. So gain 2 is easier. So therefore, oxygen will be stable when 2 electrons are gained. Gaining electrons will give us a negative charge. The magnitude of the charge is equal to the number of electrons that were gained. Okay, so therefore, O2 minus is stable. Now, magnesium, 2 valence electrons will get stability when we lose 2 electrons. Electrons were lost, therefore we have a positive charge. Magnitude of this charge is 2. And then finally the nitrogen, 5 valence electrons. We can lose 5 or gain 3. So it's easier to gain 3 electrons. Electrons were gained, so therefore negative charge. The magnitude of the charge is exactly equal to the number of electrons that were gained or lost. Okay, so that's the way to figure out if electrons are going to be gained or lost. That will reflect in the charge of the element. And remember, we are trying to mimic the gas, the noble gas configuration. Okay, very good. So now it's a good time to present the 2 different possibilities for bonding. Again, the elements will combine in order to reach the stable noble gas configuration. Different compounds are grouped in classes as a function of their bonding. We will start with 2 major classes, ionic and covalent. And we will first study the ionic bonding. Characteristics of ionic bonding. First of all, involves an element that needs to lose electrons, and we are going to label this element as a cation, has positive charge, and an element that needs to gain electrons. And this element that gained electrons we will label as an ion, has negative charge. Therefore, the composition of an ionic compound will have elements from groups 1, 2, or 13. Those are going to be the cations. Combined 2 elements from groups 15, 16, or 17, and those are going to be the anions. Okay, attention here. Hydrogen is not an element from the group 1. Okay, hydrogen does not belong to the group 1. Okay, very good. Let's see here our first example. Okay. So let's look at sodium and chlorine. So again, go to the periodic table, locate where sodium is and where chlorine is. So sodium is in the group number 1, right there, and chlorine is in the group 17. Okay. So therefore, sodium has 1 valence electron, and that's represented right here. And chlorine, group 17 minus 10, that has 7 valence electrons. Okay? So remember, when counting the number of valence electrons, you have to count everything in the last shell. And again, ask yourself if the element needs to gain or lose electrons to achieve stability. Stability means 8 electrons in the valence shell. Here. In sodium has only 1 valence electron, therefore it will be stable if loses 1 electron. Okay? So therefore 1 electron needs to be lost. Chlorine, on the other hand, needs to gain 1 electron to achieve stability. Gaining 1 electron means the charge is going to be 1 minus, and we need to gain 1 electron. Well, if sodium needs to give away 1 electron and chlorine needs to get 1 electron, that's the perfect match. They will combine. So sodium will react with chlorine, and that will form NaCl. Okay. So always when you are writing the formula of an ionic compound, the positive part of the compound has to come first, and the negative part comes last. Okay. Always plus minus. Okay. So we have here sodium 1 plus and chlorine 1 minus. And now this compound is very stable because both elements have 8 electrons in the valence. Can you do me a favor? Can you take a picture of the board and send me later? Thank you very much. Yes. All right. Okay, let's do a quick practice here. So the question here is, what's the formula of the compound formed by strontium and iodine? Strontium is Sr, iodine is I. So first thing I want you to locate this element in the periodic table. Second, figure out the number of valence electrons, looking at the number of the group. Third part, figure out the charge that each element will acquire. And final, figure out the formula of the compound formed by strontium and iodine. So let's think about that for a minute. All right, let's start with SR. SR belongs to group number 2. Therefore, 2 valence electrons. Every time you have less than 4 electrons, it's going to be easier to lose them. Okay. So therefore, strontium needs to lose 2 electrons. Again, if we lost, that means we have a positive charge. Magnitude of the charge is always the number of electrons that were lost. Iodine is on the opposite side of the table, right here on the group 17. Remember, between groups 13 and 18, we need to subtract 10 units to get the number of valence electrons. Therefore, 7 valence electrons. Every time we have more than 4 valence electrons, it's going to be easier to gain electrons. Therefore, iodine needs to gain 1 electron. Electrons were gained, charge is negative, magnitude of the charge, number of electrons that were gained. Okay, so that's half of the problem. Now we have to figure out the formula of the compound that is formed. Always start with the positive part. So we have here strontium, 2 plus, followed by iodine, 1 minus. If each strontium needs to lose 2 electrons and each iodine can only gain 1 electron, how many iodines do we need for each atom of strontium? 2, right? We need 2. So therefore, the way we are going to represent that in the formula is by a subscript right here. Okay. Therefore, you can just write like this. Easy way to do that is to cross the charges, right? The 2 goes back here, and the 1 goes over here. So every time you have 1, you don't need to write 1. All right. Come on, come on. I know that's Friday. Come on. Imagine that I can be a ton of people. Come on. Good. All right. Awesome. Nice progress here. So now let's talk about nomenclature. And we're going to name ionic compounds. So very simple rule. First one, the cation keeps the name of the parent element. So for example, when we have sodium chloride, positive part here is sodium, okay, so that's the cation. Remember that, positive. So the cation will keep its name. No changes here. However, the anion or the rest part of the compound changes. It will be the name of its parent element, except that the ending is changed to IDE. So in this case, fluorine is the anion. So we are going to change the name of chlorine to fluoride. Okay. So see here, change the ending by ITE. Okay. Sodium space chloride. Second example, SRI2. That was the guy that we just tackled there. The name for this compound, because it's an ionic compound, we start with the cation, strontium. Leave here a gap, and we are going to write the name of the anion. Okay, so it comes from iodine. We are going to replace the end by IDE. Therefore, strontium iodide. Okay, so you need to know how to write the formula, and from that, give the name of the compound. And vice versa. From the name of the compound, you have to be able to go backwards and write the formula of the compound. Thank you very much. Awesome. Questions? All good? All right. So let me tell you one thing. This course is very dense. and meeting 3 times per week is not enough. So with that being said, I will give you a lot of responsibilities. Okay? And unfortunately, we need to move fast here. But I think you can do that. It's not an issue here, just requires some work. Okay, so now that we talked about the ionic compounds, I showed you how to figure out the charge, how to write the formula, and how to name the compounds. Let's talk about the other class of compounds, and those are the covalent compounds. Starting here with some of the characteristics. Involves 2 or more elements that need to gain electrons. This kind of bond is based on the concept of sharing electrons. And covalent bonding is usually formed between elements from groups 13, 14, 15, 16, 17, 18, or hydrogen. Okay? So all this block here of the periodic table, when they bond among themselves, the kind of bond formed is going to be a covalent bond. We will not tackle covalent bonding right now, but we will come back at the end of the course, the second half of the course. Okay, so ionic bonding involves donation of electrons, and covalent bond involves more sharing of electrons. And this is how we are going to split in 2 different classes of compounds. So ionic compounds, they are basically salts, oxides, and bases, while covalent compounds, they can also be oxides, acids, or molecular compounds. Okay, so now let's talk about another class of compounds. We are going to focus here on oxides. And what I want from you at this point is to know how to name an oxide and throw the name right before. So it doesn't matter how they are bonded at this point. All right, oxides. General formula, element X combined with oxygen. Oxides are always composed by an element plus oxygen. Important characteristic here, the net charge of an oxide is always 0. Remember, the net charge of the compound is always going to be represented at the top right corner. For example, CO2 is an oxide, but CO3, 2 minus is not. Okay, so just the fact that we have a net charge here that makes this compound non-oxide. Nomenclature, very simple, guys. The first word is the name of the first element in the formula. Second word is oxide, and you are going to use prefixes to indicate the number of atoms of each element in the molecule. Attention, do not use the prefix mono with the first element. For example, CO. Let's name this compound first thing. It's an oxide because we have an element combined with oxygen, and the net charge is 0. Rules for the nomenclature. Start with the name of the first element in the formula. So we have here carbon. And the second word is going to be oxide, and we are going to use prefixes right here to identify the number of atoms. We just have one oxygen, so therefore this is going to be mono. Okay, so one mono, and then we will follow with the word oxide. Therefore, CO, carbon monoxide. Again, for the first element, if you just have one, you don't need to use the prefix mono. Second example, CO2. Again, one carbon. So therefore, we are going to start with carbon. However, now we have two atoms of oxygen. When we have two, the prefix is going to be di. So therefore, di, and then the word oxide. So CO2 is carbon dioxide. Okay, so again here, from the formula, you need to know how to write the name, and from the name, you need to know how to write the formula of an oxide. Let's move on to the second class here. Now let's talk about acids. There are two different classes of acids. First one called hydracids. The formula is HX, okay, so hydrogen combined with an element from groups 15, 16, or 17. And the second class of acids that we are going to talk about are oxo acids. Okay, so now we have hydrogen, an element from groups 13, 14, 15, 16, or 17, and oxygen. Okay, so acids are covalent compounds, so at this point it doesn't matter how they are connected. We just need to know how to name them and to how to write formulas. Okay, so let's start with hydroxide. And again, nomenclature, that's what we need to know at this point. Okay, first word. To indicate that it is a hydroxide, we use the word hydro. Second part of the first word is the name of the parent element, except that the ending is changed to IC. And second word is acid. When we are naming acids, you will not use any prefixes to indicate the amount of atoms, okay? So in the nomenclature of acids, we do not use the prefix mono, bi, tri, tetra, and etc. All right. First example here, HCl. Okay. Look at the formula of the compound first introduced to identify is this an acid, an ionic compound, or an oxide. Any compound HX, very likely to be an acid. Okay. So we just have hydrogen combined with chlorine. So therefore, we are right here in the hydroxides. The first word of the name is going to be hydro. The second part of the first word is the name of the element combined with hydrogen, in this case chlorine, but we are going to change the ending by IC. Therefore, chlorine will become chloric. So we change it here, the ending by IC. So hydrochloric, leave it a gap, and then acid. Okay, so the second example, I will leave it for you to complete. So H2S, that's a hydroxide as well. All right. Okay, I think that's a good point for us to finish for today. Next week, we will start talking about oxo acids. So again, nomenclature, it's a little more complex. And I think we will finish the chapter number 2 with that. So with that being said, that's a wrap for today. I hope you have